In November 2023, the furthest human-made object in existence suffered a catastrophic anomaly. Operating deep in interstellar space, Voyager 1 ceased transmitting intelligible telemetry back to Earth. The probe's steady stream of scientific measurements abruptly stopped. In its place, the spacecraft began broadcasting a repeating, nonsensical pattern of ones and zeros. It had effectively lost the ability to speak coherently. Because of the spacecraft's southern trajectory out of the ecliptic plane, only one facility on the planet is geographically positioned to command it: the Deep Space Network's massive dish complex outside Canberra, Australia. This diagram illustrates the physical constraints of the communication path. Voyager 1 is 15 billion miles away. A radio signal traveling at the speed of light requires approximately 22.5 hours to reach the spacecraft in a single direction. Every command sent and every diagnostic returned is subject to an agonizing 45-hour latency loop. This delay turns a routine software debug into a high-stakes battle against the fundamental physical limits of the universe. The repeating error pattern pointed to a failure within the Flight Data Subsystem, or FDS, which acts as the central neurological switchboard of the spacecraft. The FDS is responsible for gathering raw measurements from the probe's scientific instruments, formatting that information and packaging it sequentially so the telecommunications unit can modulate it for the journey to Earth. To diagnose the exact location of the malfunction, engineers at the Jet Propulsion Laboratory utilized their single uplink channel to send a poke command, instructing the FDS to execute a complete dump of its physical memory. Nearly 2 days later, the transmission returned. The forensic readout showed that roughly 3% of the FDS memory was physically corrupted and permanently unreadable. A mission that has spanned 5 decades was effectively lobotomized by a hidden failure within a single 256-word chip. Fixing the system required navigating a phenomenon known as dead men's code. The original programmers who engineered the Flight Data Subsystem have either retired or passed away, leaving the modern JPL team with heavily fragmented institutional knowledge. Designed in 1974 by engineer Jay Waddell, the FDS utilizes a bespoke, interrupt-driven architecture. To manage the data packaging, it relies on a custom instruction set utilizing only 64 basic operations. With no hardware simulators available, modern JPL engineers had to cross-reference poorly scanned assembler listings against the live memory dump, deciphering where OCR errors had swapped hexadecimal characters in the physical address maps. They were attempting to write a patch for a machine operating with a total capacity of just 8,192 words of memory. Every relocated line of code had to be accounted for manually, as any discrepancy between the paper records and the silicon reality would crash the system. The survival of the mission depended on the accuracy of these manual corrections to 50-year-old documentation. By mapping the corrupted zone in the memory dump, the team isolated the failure to a single physical hardware component, an RCA CD4061A static random access memory chip. This specific CMOS technology was originally commercialized by RCA in the late 1960s as a low-power solution for consumer electronics like digital watches. JPL selected this volatile architecture for deep space because its low power draw was necessary for a mission powered by degrading nuclear generators. After 46 years of continuous operation, the microscopic gate oxide within that single chip finally failed. It was likely shattered by a high-energy galactic cosmic ray, or slowly degraded by decades of electromigration, shifting the metal atoms out of alignment. Making the situation considerably more difficult, the only 2 existing FDS processors are currently aboard Voyager 1 and Voyager 2. With no physical testbed on Earth to validate their code, the JPL team had to execute an open-heart software surgery entirely blind. Humanity's furthest connection to the cosmos was completely dependent on the survival of a 10-cent volatile silicon component. Unable to physically replace the dead RCA chip, the Tiger team developed a surgical workaround. Instead of attempting to overwrite the broken sector, they decided to completely excise the affected telemetry packaging code. Engineers fragmented the excised code, relocating pieces into uncorrupted regions of the memory bank. Because assembly programming relies on exact physical addressing, every memory pointer was manually updated, repainting digital pathways so subroutines could reconnect across the divided blocks. The stakes of this manual pointer math are binary. A single misplaced bit would result in the permanent loss of the spacecraft. It is an exercise in low-level bare metal optimization, forcing software logic to physically route its way around hardware death. Pushing this code across the solar system required the activation of massive, heavy industrial infrastructure on Earth. To penetrate the electromagnetic interference of the solar system, Canberra's DSS-43 transmitter had to fire a 100-kilowatt S-band beam into the sky. Generating this output requires strict airspace coordination, as firing the dish presents a radiation hazard to commercial aircraft. On April 18, 2024, the transmitter fired. The code was pushed into the void, initiating the 45-hour latency countdown inside the JPL control room. On April 20, the repeating string of zeros and ones abruptly stopped. In its place, the incoming data streams snapped back into legible, perfectly ordered engineering telemetry. A bespoke architecture from 1974 managed to outlive its creators through the sheer durability of its optimized design.